Now let's see historical backgrounds of cryogenic liquids. Dr. Gori, a Florida physician, invented an expansion engine for making ice in 1840s in an attempt to alleviate patient suffering during hot weather. In 1853, the Joule Thomson valve was invented, allowing a significant amount of air to be liquefied. In 1877, a French mining engineer named Gaillet produced a fog of liquid oxygen droplets by opening the valve of an oxygen gas container at 300 atmospheric pressure. This was the first time anyone attempted to liquefy so-called permanent gas. Pictet, a Swiss physicist, developed a cascade process to generate liquid oxygen around the same time. Polish physicists Rogowski and Olszewski succeeded in generating enough liquid oxygen to analyze its properties in 1883. They also liquefied nitrogen a few days later. In 1884, Rogowski produced a fog of liquid hydrogen droplets by expanding hydrogen gas from 100 atmospheric pressure to 1 atmospheric pressure, which was pre-cooled by liquid oxygen. However, he was unable to obtain hydrogen in a complete liquid phase. Dewar, an English chemist, invented a vacuum jacket cryogenic fluid storage container in 1892. As seen in the figure, this one. This vessel is identical to modern-day thermal bottles. It was a glass vessel with two walls. To avoid heat conduction from the outside of the vessel, the space between two walls was vacuumed. So this space is vacuumed. To insulate liquid from outside heat radiation, the inner surface of the walls were also silvered. So inside this surface and that surface was silver coating. The rate of evaporation of the stored fluid was reduced by around a factor of 30 compared to an existing uninsulated container. All cryogenic liquid vessels are now referred to as Dewars, after his name, Dewar. Dewar produced 30 cc of liquid oxygen in 1898 with his vessel. This showed the early air liquefaction system. And that is schematic figure for air liquefaction system. Once, a Dutch physicist obtained around 60 cc of liquid helium in 1908. The boiling point of liquid helium is 4.2 Kelvin at 1 atmospheric pressure. His achievement revealed that there could be no such thing as permanent gas. This means that lowering the temperature of any gas will cause it to liquefy. By evaporating liquid helium, Owens was able to reach a temperature of around 1 Kelvin. He also found superconductivity when he observed the abrupt disappearance of resistance in a mercury wire at 4 Kelvin in 1911. Collins invented an effective helium liquefier in 1947. This liquefier is important for compressing the liquid helium temperature in a practical and cost-effective manner. In 1902, Claude, a French engineer, devised a practical air liquefaction system. In manufacturing his system, he founded the Air Liquide in France, the company name. Linde established the Linde company in Germany in 1879 to manufacture cryogenic liquids. In 1907, Linde built the first air liquefaction facility in the United States. On his property in Massachusetts, Goddard successfully launched the first rocket powered by liquid oxygen gasoline propellant in 1926. Dornberger developed the V-2 weapon system in 1942, and it was utilized in World War II. His rocket was the world's first large-scale liquid propellant system using liquid oxygen and 75% ethyl alcohol, 25% water mixture. After World War II, the Cold War era began. The nuclear arms race between the United States and the Soviet Union accelerated the development of the cryogenic liquid fueled intercontinental ballistic missiles, so-called ICBMs. During the Cold War, the use of cryogenic liquids increased dramatically for the sake of post-war economic success and missile development. There have been numerous cryogenic liquid mass storage containers built, as well as cryogenic liquid transport vehicles. The Atlas ICBM, which uses liquid hydrogen as fuel, was designed in 1956. The first man worked on the moon, propelled by a spacecraft propelled by liquid hydrogen, liquid oxygen propellant mixture used by the Saturn V rocket. Currently, there are also plenty of artificial satellites orbiting the Earth. Some of them are intended for military use. However, many of them are utilized for peaceful purposes like weather observation, communications, and other peaceful activities. Almost all of these satellites were launched using cryogenic liquid fueled rocket. This slide shows the rocket system using liquid oxygen and liquid fuel. And this fuel is here combined together and give the thrust of the rocket to the upward. And this figure shows Saturn V rocket. Now let's see gas liquefaction. Several expansion engines and a Joule Thomson valve are used to liquefy the gas. In an expansion engine, the adiabatic expansion process is employed to decrease the temperature of the gas. The Joule-Thomson valve, on the other hand, makes use of Joule-Thomson effect. Several expansion engines lower the gas temperature sufficiently in a gas liquefier, and then Joule-Thomson valve liquefies the gas. The adiabatic expansion and the Joule-Thomson effect will be clearly explained in the following sections. This figure shows the system of the heat liquefier. Now let's see the adiabatic expansion process in details. Since low heat is supplied to the system during adiabatic expansion, the entropy of the system remains unchanged. The adiabatic process has the following relationship, since entropy is a function of temperature and pressure. So the heat can be related to TdS, and ds S is entropy, and entropy is a function of temperature and pressure. So we can have the ds. This ds has the this relationship. So both function of temperature and pressure. So ds dt and dt, and ds dp dp. So this process is adiabatic process. So no heat is supplied, so dq should be 0. Since the heat capacity at constant pressure is defined as this relationship, so we can use this capacity expression to this equation. Then the equation above is rewritten as this equation. And here, using a Maxwell relationship, this one, apply here. The temperature change in the adiabatic process is calculated as function of pressure. So alpha S is the temperature change as function of pressure, and this can be written as this equation. So alpha S is the temperature change as function of pressure. So we expand the gas. That means that the pressure is reduced in the expansion. And also here, dB or dt at constant pressure is always less than 0. So all gas has this kind of property. So this term greater than 0. So alpha S is also greater than 0. So all gases have a positive expansion temperature coefficient alpha S. As a result, in adiabatic expansion, the temperature of gas falls as the pressure decreases. So if we expand the gas, then gas pressure decreases, and alpha S is greater than 0, so temperature of the gas is reduced. But this should be larger than 0. So if we expand the gas, then the gas pressure is decreased, so negative. This is negative. This should be positive, so dT should be negative, so temperature falls as the gas is expanded. Now let's see for ideal gas, we have the dV of dt is given by this relationship for the ideal gas. So if we put this here, then consequently the coefficient for the ideal gas is written as this relationship. In the adiabatic process, an ideal gas satisfies this relationship. T gamma B should be constant, so she is constant, and the gamma is the ratio of the specific heat at constant pressure to the specific heat at constant volume. So this gamma is 3/2 in case of monatomic gas, so inert gases, so helium, argon, or such inert gases, we have gamma equals 3/2. For other diatomic gases, this gamma should be 5/2, so different. According to the equation above, when the gas pressure decreases from P1 to P2, the temperature changes from T1 using this equation here, then T2 equal T1 and this relationship. So we use the gamma 3/2 here. If a gas at 300 Kelvin is adiabatically expanded from 200 atmospheric pressure to 1 atmospheric pressure, the temperature of the gas drops to 30 Kelvin. For real gas, the van der Waals equation is written as this equation, this van der Waals equation for real gases, and using alpha S temperature coefficient, so we can obtain a dV over dt from here. So we put this here, then we can get this relationship. Okay. Since volume of gas is much larger than B, individual gas volume, so there should be greater than 0. So this holds for any real gases, so alpha S is always positive, and the temperature of the gas decreases during adiabatic expansion. So pressure is reduced, temperature is also reduced, because alpha S should be greater than 0. The entropy temperature diagram for helium is shown in the figure, this figure. Curves depict the entropy changes of helium as function of temperature in isobaric process. So there's some isobaric process curves, and this number represents the density of gas, and this y-axis temperature, and x-axis entropy. And this region is the two-phase region, So gas and liquid coexist in this region. Gas and liquid coexist in the two-phase region, this region, blue region. When helium gas is adiabatically expanded from point A here, so this curve, higher density, to point B, low density, expanded. So your density of gas is lowered, so it means gas is expanded from 7 to 1. Then its temperature is decreased to 2.5 Kelvin. So this temperature is around 2.5 Kelvin. And the sum of gas becomes liquid, goes to two-phase region. So sum of gas becomes liquid. If the gas is adiabatically expanded from C to D, however, from here 3 to 1, so starting from here, expanded to 3 to 1, but the gas is still in the gas region, not in the two-phase region. So the final state D does not exist in the two-phase region, and hence no gas can be liquefied.